So as you can see here, review number 7 is pretty much just all the integration methods that we've done throughout the year. Some of these won't be quite as important with it not being multiple choice, but as we work our way through, I'll kind of point out what would tend to be something on a free response test. But you just want to know it all. Just have no idea really how this is going to play out and what types of questions you would see relative to what has been going on for the last 20 years. So just the first page and a half really just outlines all the things all the different methods of integration we have done throughout the year. So the first one here is just our power rule, knowing that we add 1 to our exponent, and then we would divide by that we should know. The trig antiderivatives, again, you have to know those. I don't think that's something that we need to spend a ton of time on. Certainly have those memorized and down pat. U substitution, we're going to have an opportunity here working throughout the packet to see some U substitution ideas. So we'll do plenty of those, but this is kind of the order in which we did them. Basic power rule. So we did power rule, antiderivative or trig functions, then we did some U substitution. We also then did, the big ones here are going to be the E and the natural log. I don't see how they don't test you on those couple things real quick. Can't imagine they really give you much of these. I wouldn't spend a ton of time on that. Again, be prepared for everything, but the exponential function and the natural log function and how we come about getting those are the big ones. The inverse trig functions, just knowing that 1 over the square root of 1 minus x squared. If we did that antiderivative is inverse sine. That's something. I'm going to give you a formula sheet. Probably a few days before that AP test, I'll attach it, send it out somehow, either remind email or through Skyward Messenger, and I'd have all that in there, have that handy in case something like that were to pop up. Once we get to these now become all the BC specific topics. So these would be the ones for sure to know. Integration by parts is BC specific. We'll go through all of that. It's typically a product. So x times a cosine of x squared times e to the x, that we can't do through U substitution. So if you have a product, U substitution doesn't work. That means you're probably dealing with integration by parts. Be careful of the ones where neither one of them repeats. I can't imagine, again, that's going to be something that they're going to test you on. It's a very, it's a very specific question that I don't think they're going to really try to test you on. I wouldn't spend a ton of time on that, but certainly these types you're going to want to know. Also, free response wise, if you have to do an integration by parts, they're going to want to see, it's very rare on the free response portion, but they typically want to see the work for this. So make sure you're going to show that work. If you're going to do tabular, make sure that you're doing that. I'd strongly recommend doing the integration by parts just so they know where all of that stuff were to come from. But that's a pretty common free response idea. These are another one that I just can't see how they're going to put that on there. I don't think this really tests, a broad scope of what we have learned. But, to cover yourself, just make sure you know these. All the ones I've seen, they typically include these first couple. Never really seen a double angle formula. Never seen an identity where we've had to use the 1 plus cosine 2x, 1 minus cosine 2x identities. It is it has always been one of these three when they do test on these. Never seen that as a free response question. Integration by parts, definitely BC topic that you'll want to know. We'll do plenty of those here. That's pretty easy. There's really just one type of those questions that you'll want to be careful of. And then the improper integrals when either your limit, 1 or 2 of your limits is infinity, or if we look here, x can't be a 0 in this function, but 0 falls within the interval in which we're trying to integrate, or basically that function is 1 over x. If you think about what that graph looks like, we're trying to find the area from a -1 to 1. And we cross a place here at 0 where our function is unbounded. So that's another way we get an improper. Okay, so we'll go through, point some of the big ones out. I'll leave you some answers for some of these so you can do those on your own if you'd like. This is one that typically, when we do meet in the evening, we can go through fairly quickly because most people will remember these. So when you see a fraction, so we have a fraction here, U substitution if we can't just look at it and know our antiderivative is always your first option. Don't skip over that. This one looks like u substitution may work, where maybe you do u is a x squared minus a 3x plus a 2. When you take your derivative, you get a 2x minus a 3. We needed a 5x minus a 7. There's really no way to manipulate this to create a 5x minus a 7. So when we try u substitution and it doesn't work, and you were dealing with a quotient, what that tells us is we're probably dealing with the partial fractions method. So that was the method where, let me do it over here, where we would factor and try to figure out what were our two numerators that were over these linear factors, x minus 2, x minus a 1. So we just worked our way through that. We're going to get a common denominator on the left, common denominator on the right. Our least common denominator for this would be the product of x minus 2, x minus a 1. So the a over here was missing the x minus a 1. So that would get multiplied by x minus a 1. The second fraction is missing this x minus a 2. So we're going to do the b times an x minus a 2. And then this had both factors, so we can just rewrite that as 5x minus a 7. Here we go. From there, it just becomes some algebra. So we'll distribute our a, distribute your b. Then when we first did these, we were pretty thorough. We said let's rearrange so that our x terms are written consecutively, and then the constant terms, the non-variable terms, are written in order. We said then we'll pull out the x. We're going to put the x behind that quantity, and then our constants are the negative a minus 2b. And then since these are equivalent statements, the coefficient of x over here would have to be equivalent to the coefficient of x on the left-hand side. So we know a plus b would have to equal 5. These are the constants on the right-hand side. This is the constant on the left-hand side. So those would have to be equivalents as well. We always end up with a system with these. If we notice, we can add these two equations right away. When we add the equations, the a's are going to cancel each other out. So what we would be left with is a negative 2, and then we have a negative b. So our b would equal a 2. Once we know that b equals 2, if we look back at this equation, a plus b had to be 5. So what that would tell us is our a needed to be 3. So then what we did, we would go back to the original, I guess not quite the original problem, but once we had that factored, we now know that our a was a 3, and we know that our b was a 2. These now become very simple to integrate. This first one just becomes the natural log of the absolute value of x minus 2 with the 3 out in front. For response-wise, absolutely make sure you're putting these absolute values here. That's something you'll lose a point for. Plus, and then this would be 2, the natural log of x minus a 1. All right, and then add your constant. 2, I like to put this one on here because if this was just secant squared of x, and we wanted the antiderivative, then right away we can jump to a tangent of x, and then our constant. The fact that this is x plus 2, technically when we did these antiderivatives, if we didn't have a simple x, like we would do right here, this would be a u substitution. What you want to understand, just to save yourself some time if this were to present itself, if you let your u be an x plus a2, which is what we would probably want that to be or need that to be, the derivative of that is just a 1 and then dx. If in u substitution you take the derivative of your u and you get a 1, what that tells us is we really don't get anything extra out of this. There's going to be a 1 always. That's never anything that we can't handle. What that means is we don't really need to do u substitution to deal with this problem. This would basically behave the exact same way as this one up here would have behaved. So we can still, with this one, jump right to x, tangent of x plus a2, and then plus our c. Okay, so just be aware of that. It's the same thing with like the 1 over x plus a 7. If this wasn't here, that's a natural log. The fact that that's there doesn't change anything. It's still a natural log, but of now x plus a 7. All right. 3, you have a product. If we can't look at that product and know the antiderivative immediately, we go through our steps. The first step is u substitution. So if we think about what we would probably let u equal, 7 minus x to the 5th. Take your derivative, a negative 5x to the 4th dx. Notice what we wanted. We would have wanted an x to the 4th and a dx. We got that here. So that negative 5, we just can divide that over and create the x to the 4th dx terms that we needed. So then u substitution worked. If it didn't work, we deal with products using integration by parts. Okay. With this one then, we have u to the 3rd power. That was what our u was, the inside part of that expression. X to the 4th dx we have here, so we can get rid of those two items with a negative 1/5 and a du. As long as you get everything in terms of u and end up with something that's easy to find the antiderivative of, which we can check both of those boxes, we go ahead and do the antiderivative. And that should be your answer. And in this case, u was what? 7 minus x to the 5th over 20. It would all be negative, and then add your constant. Okay. 4. Another one that you, again, don't want to jump over u substitution, because this is u substitution. U would just be x squared plus a 1. Du is a 2x dx. We needed an x and a dx. There's a couple. So the only thing that's really differing right now for us are the numbers. A couple different options. We could, if we want, take this 4 and pull it out in front. And then if we look at this, we would say, all right, if all I want is this x dx, I could divide that half over and get the x dx that we need. And then that would ultimately put a half in front, so our coefficient ends up being a 2. That's a viable option. That's probably the safest option if the numbers aren't nice. Maybe it's an ugly fraction or whatever. This one is not too bad to go with the second option, where if we say we actually want 4 with the x and the dx, then it's pretty simple to do that. If we just multiplied both sides by 2, so that we would say twice du would now equal 4x dx, it's not hard for us to turn that into a 4x dx. We just know we're going to get a 2 du. So either method, what we would ultimately end up with is a root u in your denominator, a du here, and either way, there would have been a 2 as a coefficient. All right, to get rid of the 4x dx. So if we want to get rid of these, we would need to replace them with the 2 and the du, and we would end up with that either way. Keep in mind, this is not a natural log. The natural log has to be 1 over u to the 1st power, or 1 over x, like this one up here had a power of 1. That's the only time you will be creating a natural log. This is the old power rule. Bump that up so it's u to a negative half. Oops. And then add 1 to that power, divide by that power. So that we would get 4 root u plus c, replace your u with the x squared plus 1, and then that should be our answer. Okay. 5, another u substitution. Natural log of x is our u. Du is 1 over x times dx. That's exactly what we wanted. We would have had a 1 over an x and a dx. So this would just be a u cubed, and then the 1 over x dx would be gone when we replace it with our du. All right. Similar to the previous problem, this is just an old power rule idea. Bump that up to be u to the negative 3, add 1, divide by that new power, add your constant, and then that's pretty much our answer. This would ultimately be a negative 1 over 2, that's the negative half. Put that u squared in your denominator, replace your u with the natural log of x, should be good. This question, I put this on a partner assignment, if you remember this, before we left. Looks tricky. Pretty much anytime we're dealing with one of these, your u would be the exponent. If we understand that the cosecant, being divided by a cosecant, is the same as being multiplied by a sine, then this is pretty simple. your u is cosine of x, your du is a negative sine of x, and the dx, notice there is no negative here, so we would divide that over, leaving us with a 2 still, raised now to the power of u, and then the sine of x dx we have right here, we would get rid of that with negative du. So antiderivative of this is 2 to the u, and then we would divide by the natural log of the base, and then if this had a coefficient, suppose it does, it's a 1, we would also need to divide by that. But in this case, with it being a 1, no need to show that. Final answer would be a negative 2 to the cosine of x divided by the natural log of 2. All right. 7. We know how to do identities now. It's one of the ones that we just talked about here in that first page and a half. But if you notice, we don't want to skip u substitution. This actually is a test question. This is on your test. Some of you might, or something very similar, where some of us made this very hard with identities, where we could, and with the trig functions raised to a power, a lot of times just tell you to rewrite this. It's a little easier to see. Then we see that the inside is your u, which is usually what our u is going to be. The derivative will give us that cosine of x and then the dx. So this is u to the 4th. Oops. And then the cosine of x dx we created right here. It's equivalent to our du. So we can get rid of cosine of x dx with our du. From there, pretty simple. All right, u to the 5th over 5. Replace your u with sine of x. And then that's our guy. All right. Before we do number 8, jump on down to number 11, because it's going to pop up in this next problem that we just skipped. This you'll just want to have memorized. If you don't get it memorized, again, you're going to have, there's no reason not to have this. Write it down somewhere. I'm going to try to give you a document where all this stuff is handy so you can just look at it real quick if this were to pop up and you didn't know it. You could do u substitution here, rewrite tangent to sine over cosine, let u be the cosine of x, and then work your way through substitution. That would be silly and wasting a lot of time. This we know is the negative ln of cosine, and it's the absolute value. Or with it being multiple, with it being multiple choice, you don't have to express that. But that could be written as a natural log of secant as well. So keep that in mind when we come back up here to number 8. 8 is the first one where you have a product. So we've had a number of products up until this point, but u substitution is not going to work. If we try to let u be a 2x, the du just gives us a 2 du. We don't get rid of this x. If we try to let it be some combination of a secant, the derivative of secant is going to give us, secant tangent of some sort. There is no tangent in this. So u substitution with this product won't work. The next then step for products is integration by parts. Remember when we did integration by parts, we said most of the time you want the u to be the term that's derivative would eventually go away. So I'm going to make that for x. The dv will always contain the dx. And what we still have left over is a secant squared of 2x. We would then take the derivative of u, giving us 4dx. We would do the antiderivative of our dv. That would be the tangent of 2x. And then we'd have to divide by that coefficient. So the antiderivative of this, you have the formula written out on page 1, is u times v. So that's the 4x times the tangent of 2x over 2 minus the integral of v du. So that would be the 4, and then up here's your v. So 4 times a tangent of 2x over 2, and then our dx. So let's clean this up real quick. This would be 2x tangent of 2x minus the integral let's do 2 first. These are going to cancel or reduce. Minus 2 and then the integral of tangent 2x dx. As long as this has an antiderivative, then we're set. The next step should be your answer. The 2x tangent of 2x is all set, minus 2. And then the antiderivative of tangent we just did at the bottom here is a little refresh, is a negative natural log of cosine of 2x. And then we would have to divide that by the coefficient of the x, which is our 2. We squeeze in a plus c. Second one, I guess it simplifies a little bit. The negative and the negative would make positive. The 2's are going to cancel each other out, and we would just end up with a natural log cosine of 2x. All right. So that's our first integration by parts. Again, BC specific topic. That is one that's fair game come that day. Number 9, I think I'm just going to tell you to not worry about. It is an integration by parts, but then as an integration by parts, you'll have to do U substitution at the end. Just not going to happen. They won't do that to you. So we'll save you some time and some effort and not overload you with things that probably aren't going to be on there. 10, however, definitely a big deal. We didn't learn how to do the antiderivative of a natural log of x until the integration by parts because it required that method. So some combination, we'll talk about what that is down here, number 12. What is the antiderivative of ln of x? You'll want to have that memorized. But if you look, here we have a product. No combination of U substitution is going to work. So it is another integration by parts. I set up here, your U is typically going to be the term in that product that has a derivative that would eventually turn into 0. So for us in number 8, that was your 4x. That is a general rule. That rule is usually trumped when you have a natural log involved. So what that would mean is our general rule would say we'd probably want U to be an x cubed and then the dv to be the natural log of x. You can get through that way, but it's pretty tricky. When there is a natural log involved, typically that trumps that rule, and we want our U to be the natural log. So we're going to go that route. We know we need the derivative of the U, so we'll do that. We want the antiderivative of our V. So antiderivative x cubed ln of x dx is equal to uv. So that would be the x to the 4th over 4 times the natural log of x minus the integral of v du. So that would be the 1 over x dx times x to the 4th over 4. Clean that up real quick. Oops, that's a product. This reduces down to be x cubed over a 4. And this then we have an antiderivative 4. So we get x to the 4th over 4 times ln of x minus x to the 4th. Then we'd have to divide by the new exponent of 4. We would have already had a 4 in our denominator. Gives us a denominator of 16. Add our constant. 12. Memorize this. Again, in a 3-hour and 15-minute test, this would always be on there. Hard to say for sure now, but just know that antiderivative of ln of x is x ln of x minus an x plus your c. Okay, 13. It's another integration, or sorry, partial fractions. You could try U substitution. Actually, it looks pretty promising, where if you let U be x squared minus 7x plus 12, and then took the derivative to get a 2x minus a 7. Close, but there's no way we can make that 2x minus a 7 into a 2x plus a 1. You'll notice it's a fraction, however. You'll notice that it does factor nicely. That would lead you to believe correctly that this is a partial fractions problem. So we'd factor this, x minus 3x plus 4, and x minus a 4. So our 2x plus 1, the a is going to get multiplied by the x minus a 4, so we would get ax minus 4a. The b has to get multiplied by the x minus a 3, so that would be bx minus 3b. We would group them. So here's our variable terms. So we would have the a plus b added together. That sum is the coefficient of x. And then the non-variable terms, negative 4a minus 3b, must be our constants. 2 would equal a plus b. And then the 1 would have to equal the negative 4a minus 3b. This now requires a little bit more effort in terms of evaluating a system. Really up to you. I prefer elimination. For me, this might be easier to do with substitution. Sort of up to you. I just like elimination, so I'm going to do elimination. So I'm going to multiply that first one by 4, so we get 8 equals 4a plus 4b. And then in the second one, we can just rewrite it. 1 equals a negative 4a minus 3b. We can see now that if we add these two equations, we would get 9 equals. The a's cancel, which is our goal. Add the b's, and we're going to get our b's to equal 9. If we revisit this equation here, where a plus b has to equal 2, then pretty quickly we would see that a would need to be a negative 7. We can then go back to the factored version up here. We now know a is the negative 7. We know b is our 9. Both of these are our natural logs, so negative 7 natural log of x minus a3 plus 9 the natural log of x minus a4. All right, plus c. 14, pretty tricky stuff. I didn't even really do this with you. I usually do a few of these at the end as a, just in case scenario. That's what we'll do now. I would not fret on this too much. Just can't imagine they would give you this on a free response question. Even if it was multiple choice, no one's ever come back saying they needed to do this. But it is explicitly written in something you're supposed to be able to do, so we'll talk about it now. If you try use substitution, it doesn't work. There's really no option for use substitution. So we can eliminate that option. Typically then, if it's a fraction, just like number 13 was, it would factor and it becomes a partial fractions problem. Try as hard as you'd like. There's no way to factor x squared plus 4x plus 5. It looks really close because of the 5 and the 4. You look at it and think maybe there's some combination that would work. It doesn't. So what this is, it's sneaky, first of all, but it is something you are supposed to be responsible for. If you rewrote it, notice how I kind of left a little space in here. So one of the things you're supposed to be able to do is understand completing a square in order to do an antiderivative. So what I'm going to do, I split these up a little bit. I'll put a parentheses here. I'm going to put a parentheses here, and then I'm going to add a term that would create a perfect square. If you remember how we create perfect squares, we would take this middle term, the linear term, divide that by 2. That gives us a 2, and then that result you have to square. That's what should go right here. So that ultimately leads us to a value of 4. When you would have done completing the square, if you had an equation, if you add 4 to one side, you would have to add 4 to the other side. So we're adding the same thing to both sides. If it wasn't an equation like this one, it was just an expression. Then to account for the fact that we just randomly added 4 out of thin air, we currently have changed our problem. What we would then have to do over here is subtract 4. So that what we really added is nothing. It's just allowed us to rewrite this integral. So what we would now be left with is still that 1 on top. This now, the whole idea behind completing a square is we create a perfect square trinomial, which factors down to be x plus 2 times x plus 2. And then what we would have here is a plus 1. Some of you may still be looking at this, wondering what good does that do us? But what this has now set up is this guy. 1 over 1 plus u squared. The antiderivative of that is our inverse tangent. And that's what we've just set up here. This technically is a u substitution problem where u would be an x plus a 2. But like we talked about earlier, the derivative of your u is just a 1 dx, meaning we don't really need to do u substitution. We can do this as if this was just a regular x squared versus an x squared plus 2. So this, don't need that anymore. This antiderivative is just the inverse tangent of u here's your u, x plus 2, and then plus your constant. So the ability to complete a square to make an integral something that we can handle is technically a topic. No one's ever come back saying that they needed to do that. Wouldn't spend too much time on it, but if it happens, there you go. 15, I am going to just give you that one. There's probably no need. We've already done a number of these. This is another partial fractions problem. I'll give you the answers. If you want to make sure you can get through one of these on your own, feel free. So 3/4 ln of x minus a3 plus 1/4 natural log of x plus 1. All right, and then our constant. 16. Just a real quick one, just a little refresher on how we do the antiderivative of this. As you know, e to the 2x, e to the 4x, really just e to the kx. Notice how there's a power of 1 here. The antiderivative of that, it repeats itself, and then we would divide by that coefficient of x. So for this one, e to the 4x divided by 4, and then plus your constant. 19, we're going to skip. Again, it's an inverse sine function. Another one that just is not going to appear. But that would be our answer. If you really want to try to work your way through that, that's pretty hard. 18, this is an exponential function. So similar to, can I get them both on here? Number 16, where it's going to repeat itself, and you've got to divide by the coefficient of x, a 2. So right now, we've done the exact same thing. What's different about these, if you know, this is the exponential function when you actually have the e here. This is still an exponential function. You have a base that's a constant and it's raised to a variable. So that's why it behaves just like this one does. But if it's not an e, we've also got to divide by the natural log of the base. Then our constant. We really can do that up in number 16 as well if you think about it. We really could divide by the natural log of the base here, and then we're doing the exact same thing in 16 as we did in number 18. The reason we have to show it in number 18 is the natural log of 6, nothing fun happens. Whereas in 16, the natural log of e, we know to be 1. And since we would just be contributing a 1, extra 1 in our denominator, it's not needed. All right. Again, that just something to know, so that we can get through that pretty quickly. 19, another partial fractions. I feel like I was partial to partial fractions on here and put a lot of them. So let me give you this. Another one that if you want to make sure you can get through, here you go. I simplified it a little bit just so you remember what this would have been is 1/2 the natural log of x minus a4 minus 1/2 the natural log of x minus a2. That's our answer. It's free response. Not necessarily probably something you would have to simplify, but if you did, we would have to recall that if I am subtracting 2 natural logs, I can create 1 natural log if I divide their composites. So that's how we ultimately get to that simplified answer. 20, though, I do want to go through. This is a type of question that was on your test in this chapter that a lot of people missed. It is commonly tested. It is commonly missed. If they give you one, it would likely be this. This was a free, this not this exact one, but this topic was a free response question a couple of years ago, and it definitely was this type. We have a 2 in front of one of our x's. All right. The big thing here, I'm going to trust that you can kind of do the algebra, go through all that work. We've done it 3 times already. There's already a couple that I've just left the answers to. The algebra here isn't going to be anything challenging. If you wanted to make sure, you should have gotten a 4 to go over the 2x minus a3. And then you should have gotten a 7 to go over the x plus a 1. So if you wanted to pause me, make sure you can do that on your own. Feel free. But it's no different than the problems that we've done already today, a few of them. And typically this is not something that people have a hard time with. What is different about this one, and what you have to be very, very careful of, because this is usually the route that they take when they give you a partial fraction problem. Both of these are going to be natural logs. This has a power of 1. This denominator has a power of 1. So both of them, for certain, are going to give you a natural log. This would be the natural log of x plus a 1. this will be the natural log of 2x minus a 3. The 4 is our initial coefficient in the first one, and that 7 is our initial coefficient for the second one, and then we're going to get our c. Actually, this was the question from your test on this chapter that a lot of people miss because a lot of people pick this answer. The reason it is not this answer, if you recall, remember how this one has a coefficient of 1. This is, again, technically a u substitution problem where u would be an x plus a 1. But when we do our derivative, we just get a 1 dx. The 1 tells us there's really nothing we need to be concerned about in our antiderivative that we need to deal with. So we can just put that 7 as a coefficient, take our natural log of the x plus a 1. Our issue with this one is, since this, again, is a u substitution problem, think about if we actually carried out that substitution, du would be a 2 dx. Well, we have a 4 dx. Like the one that we did earlier where I said you could just multiply both sides by 2 in order to create the 2. That would work. When we did these, what we always did, so again, it's up to you what you would prefer. Let me get this back. But what we talked about when we did these was if we had a coefficient of 2 here, we would know that we would then because if there was a 2 here, we'd have to divide that over, is we would just know we need to divide that coefficient over, and our coefficient ends up being a 2. Just be aware of that. That's how they would try to get you with one of these problems, okay? So don't fall for that old calculus trick. Next thing we did, we did these improper integrals where one of your limits is infinity or both of your limits are infinity. That is typically the one they're going to do. So if you look at 21, 22, 23, that's all those. The other one they'll try and do is here's one where the x can't be a 0, but definitely falls within our interval that we have to integrate between. So that's also an improper integral. Typically, though, you're going to get one with infinities. So first and foremost, you have to be able to handle the antiderivative. It doesn't do us any good if we don't know how to find the antiderivative of this, all right? Actually, I should say that's the second thing. The first thing we would need to do, especially since this is all free response, is we're going to replace our infinity with a finite value, which we're going to call b. And what we're going to be doing is calculating the limit as b approaches the value that's causing our issue, which in this case is infinity. So we turn this into a limit problem, and we're going to approach the value that makes this thing a problem, makes it indeterminate or undefined. So when we look at this, our method here is going to be u substitution. I'm going to write this as t to a negative 1. Actually, just so make sure we know where that came from. We're going to say our u is 1 over t. It's the inside term here. Then I'll rewrite it as t to a negative 1. If we took our derivative of this, we would get a negative 1 t to a negative 2, and then our dt. Notice how your sign is positive. We wouldn't want the negative sign. So in this next step, I'm going to multiply the negative over. And then I'm going to put that t squared into my denominator with a positive exponent of 2. So we'd be left with this. So we know that our 1 is now going to be positive. So that's what we needed to get rid of. We needed to get rid of, let me get rid of these little marks. We had a 1 here. We had a t squared in our denominator, and we have a dt. And that's what we have. We have a 1 in the numerator, t squared in our denominator, and then our dt. So we can get rid of all of that if we replace it with a negative du. So what we ultimately would just end up with is a negative sine of u and then du. From there, we'll do our antiderivative. So this is a cosine of u. We're going to evaluate it from 2 over pi to b. And again, we're looking for the limit of this as that b gets larger and larger and larger. So we don't want to drop that out. That should stick around. Plug in your upper limit minus your lower limit. All right, and then now I just realized that I'm doing some really bad stuff, so I apologize. And this is important because with them being able to see your work, they would definitely, I just lost my perfect score so far on the test because this would cost us a point. So let's revisit some things here. When we do U substitution, so right here, U is equal to 1 over T. These values here are values of T. They're meant to be substituted in for that value, all right? So as soon as we then switch from T's to U's, our limits would also have to change. So at this very next step, I really need to, they can see your work, you would need to do the same. We need to change our limits. This was a B, so this would have been B, the infinity. U would then become a 1 over B. All right. Then 2 over pi, if I substitute that in here, my lower limit becomes a pi over 2. Okay. As soon as our t's become u's, our variables need to change accordingly. So that would also mean here, let's rewrite these guys. So this is now 1 over b. This would now be pi over 2. Same here. We don't then need to substitute back in what u is. We're just going to plug in our upper limit, which should have been 1 over b. And then here we plug in our lower limit, which was pi over 2. We know the second one, the cosine of pi over 2, the x coordinate at the top of our circle, going to be a 0. So then it's just going to depend on what happens as b goes to infinity. So this is now, we've been doing this a little bit here with the sequences and series stuff. As n goes to infinity, in this case it's a b, your denominator here is going to be getting bigger and bigger and bigger and bigger. So this would become 1 over 100, 1 over a million, 1 over 2 million, which would mean overall then this is going to be getting smaller and smaller and smaller. So that 1 over b starts to behave more and more like a 0. So make that a 0, which would then take us to the value of cosine of 0. The cosine of 0 then is a 1. So what we would say is this converges to a value of 1. The work here is pretty critical just because they would be able to see it, and we want to make sure we're doing it mathematically correct throughout. So those substitutions, make sure you're clear on that. I'll be better with number 22 because this is also going to be a U substitution problem. So first thing, we would want to rewrite this as b, and then 1 plus x squared dx. And then say we are now calculating this as a limit problem. What happens as our b approaches that infinity? U substitution wise, we want u to be a 1 plus x squared. Du would then be a 2x multiplied by our dx. We just want the x and the dx here. So x and then the dx, we have that, but the 2 we're going to need to divide over. So go through those steps. So in this next step, we want to calculate what's going to happen as b approaches the infinity that's causing the problem in the original. Our new lower limit, we're converting that right here. So it was a 1. If we plug that in over here, our new lower limit is going to be 2. Our upper limit was b, so we're going to plug that in over here, giving us an upper limit of 1 plus b squared. Your denominator would now be u squared, since u was the 1 plus x squared. And then to get rid of the x dx, we would need a 1/2 and a du. So I'll put the half in front. So that leaves us with this. Let me rewrite that one more time with a negative exponent. So we now want the limit of this integral as the b goes to infinity. So we write that as u to a negative 2. We'll go through now our antiderivative, that whole process. So this would be u to a negative 1 over negative 1 from 2 to 1 plus b squared. So this would be negative 1/2 times 1 over u. And then now, running out of room, let's evaluate this. I guess I had a little room. I'm going to leave that negative 1/2 alone out in front. I'm going to ignore it. Then I'm going to get 1 over 1 plus b squared in my denominator minus 1 over 2. From here, evaluate now what happens as b goes to infinity. We have this, we have this negative 1/2 out in front. If b is going to be getting larger and larger and larger and larger, this denominator here is getting bigger and bigger and bigger. So we get 1 over basically infinity. Takes this whole fraction down to a 0. This converges to 0. This would remain a minus a 1/2. So overall, what we would say is this integral converges to a value of 1/4. 23. We'd rewrite this as a b, and we want to know what happens as b goes to infinity. We've seen this now a couple of times today. This is your inverse tangent. So we can jump right to that. No substitution needed, no fancy method of integration. This is just the inverse tangent of x from 0 to b. No need to change limits in this case. We never had to do u substitution where we went from x's to u's. It remained x's the whole time. Plug in your upper limits. So let me write the limit first as b goes to infinity. So upper limit minus your lower limit. Inverse tangent of 0 is 0. And then this you just have to remember a little bit. This is pretty common. As b goes to infinity, think about the inverse tangent graph. Here's what that inverse tangent graph looked like. And it does level off towards a limit right here. And that limit has to be pi over 2. So as this goes to infinity, the inverse tangent converges to pi over 2. Subtract our 0. We would say this converges to pi over 2. Okay, last one of these types, the improper. This one we've done also, at least some variation of this. Let me rewrite this first. Hold on. Get rid of all that. First, I'm actually going to say x cannot be 0. And if you look, 0 definitely falls in the interval that we're trying to evaluate this integral. So we're going to set up a negative 1 to b with x to the negative 2/3 as our function. And we want to figure out what happens as we approach the value that makes us undefined, which is a 0. We would also then want to do the same thing on the other side. This we would be approaching 0 from the left. This we're going to be approaching our 0 from the right. And we'd be going from the b to a 1. Same exact function though. We're going to do this one. If this one converges, then we've got to do this one. If the first one diverges, we don't have to worry about the second one. So antiderivative first. So our limit, as we approach the 0, that's our problem. We would get antiderivative to be x to the 1/3 divided by 1/3, so times 3, from a negative 1 to b. This is just from the left. So as b approaches 0 from the left, pull the 3 out, plug your upper limit in, so this would become the cube root of b minus the cube root of negative 1. Well, as b gets smaller and smaller and smaller here, we basically get a 0 inside of that radical. The cube root of 0 is going to be 0. So overall, this converges to 0. So we would have a 3 getting multiplied by what is becoming a 0 minus, and then we can do the cube root of 1, and that would be a negative 1. So somewhat unfortunately, this first one converges to 3. And then what we'd have to do is add that to this one if this one also converges. All the same steps. We now want to figure out what happens as I approach the 0 from the right. We would still get the same antiderivative, x to the 1/3 divided by 1/3, so times 3, from b to 1. Upper limit gets thrown in there, so we get the cubed root of 1 minus the cubed root of b. What happens is as b becomes 0 from the right, same thing that would have happened from the left, this guy here is going to be going to 0. And what we would end up with is this 3 getting multiplied by the cube root of 1, which is a 1, and then minus that 0. So this one also converges to 3. So overall, we converge to 6. All right, so then last but not least, another one that I really can't see them doing much with on a free response question. It would just be some random kind of C, D, E question to see if you know it. But this is kind of the last thing we've done where you had to do all those identities. They would not get too creative with this. These are tricky because there isn't necessarily one set method that always works. Most of you think partial fractions is easy. Most of you think integration by parts is pretty easy because it's pretty much the same thing for every single problem. When we deal with these, it's really just a little bit of guessing and checking, some educated guessing, hopefully, but you don't necessarily know going into it. So with this one, what we talked about is a couple things. Odd powers are not good because we have no substitutions with odd powers of 3, 5, 7, and so on and so forth. So typically, those don't provide us with a lot of options. So odd powers aren't necessarily a good thing. When we're dealing with sine and cosine, eventually, most of these do turn into, at the end, some sort of a u substitution problem. So if you're going to be dealing with a sine or a cosine, the derivative of sine would give you a cosine. If you pick u as the cosine somewhere along the way, the derivative of that is going to give you a sine. So it's good to kind of have a single term, a single sine or a single cosine, so that if we pick our u as the other one, the derivative would get rid of that single sine or cosine. That's what's going to guide us here in terms of getting this one started, are those two things. So that sine cubed, I'm going to rewrite as a sine of x, and then I'll do sine squared of x, cosine squared of x. Probably what most of you would have done anyway. We now have a couple identities at our disposal for both of these. There's a couple ways we could write sine squared. There's a couple of ways we could write cosine squared. What we would probably want to do, notice how we have this single sine of x. If we could somehow make all of these a cosine, then what would hopefully happen if we let u equal a cosine through substitution, we can eliminate all the cosines. They would all become u's. And then our derivative, even though it's a negative, would take care of that single sine term that we would have right here. So that's kind of our thinking. That's how we want to progress with this next step. So I'm going to leave the sine of x alone. Sine squared would become, there's a couple options. We're going to do 1 minus cosine squared, and then that just makes everything a nice cosine term, right, or cosine squared term. Sometimes we want to distribute. Sometimes you don't need to. If you remember, sometimes we want to split up the integral. Sometimes we don't need to. This one, you're really ready to do this right now. If you let u be that cosine of x, and then that du would give you the negative sine of x dx. We know we don't want it to be negative, so we're going to multiply that over. All right, so negative du equals sine of x and then a dx. We look at what we have left over. This here would have become a 1 minus u squared. Here is another u squared. And then sine of x dx we would have still had. So here's our sine of x, here's our dx. We can get rid of both of those with a negative du. If we get rid of every x term, and get it in terms of this case into u with something that we can handle, then that means we probably did it right. Here we would want to now distribute this before taking the antiderivative. So it'll be the negative of these two guys' antiderivative, which would be u cubed over a3 minus u to the 5th over a5 plus your constant. Final answer then is negative, and then u is a cosine. So we get cosine cubed of x over 3 plus cosine to the 5th of x over a 5, and then plus your constant. All right. Those are all your methods of integration. Hopefully you remember most of that. That typically is a review. This one was a little shorter than some. That goes pretty quickly, that we still have a pretty good grasp on. The big ones that we didn't typically do particularly good on are these improper integrals. If we were to go back and revisit, I don't know what just happened here, go back and revisit this test. This was the test that some of us didn't do so good on, and part of it was these improper integrals. Okay. All right. So with that, this is 7. We really only have 2 left, and the last one being the sequences and series information. So there's really just one topic that we need to review and treat it as a review, because review number 9 is something that we just got done doing. So that still should be pretty fresh. So I'll get that posted in the next day or two, and then you, for the most part, will have everything at your disposal. If you have any questions, reach out. Again, hope everybody's well.